Today's topic for the notebook is fractions. As always, we'll start with the main takeaways, and first up we have adding or subtracting fractions. As with anything in mathematics, when we add or subtract, we can only combine like things. With fractions, you may have heard common denominator. So here we found our common denominator, and that will be our denominator for our answer. And for the numerator, we're just going to straightforward add or subtract as given. For multiplying fractions, this is pretty straightforward. We just multiply the numerators, and that's our numerator. We multiply the denominators, which will be our denominator. For dividing fractions, you may have heard the term keep, change, flip. We keep the first fraction, change, divide to multiply, and we're going to flip this fraction. And then it becomes a straightforward multiplication problem. B times C for the numerator, A times D for the denominator. When raising a fraction to an exponent, you're simply going to distribute both in the numerator and the denominator. Let's look at some examples. So I have these exclamation points here in adding and subtracting only, and the reason is because for adding and subtracting, you must combine like things. Therefore, you're going to end up with the same denominator, and when you add or subtract, you just keep it the same as whatever you're given. So for our example, we have 4 halves plus 3 halves. That's going to be 7 halves. An improper fraction is anything greater than 1, and so if you're asked to turn an improper fraction into a mixed number, we have 7 halves. So I can use 6 of those halves and make my wholes, and that will leave me with 1 half left over. Here we have 4 of something minus 3 of something. That will give us 1 of something, and in that case is halves. And you can look at that in action. Put some half moons up here. I've got 4 half moons, and I take away 3 half moons. I'm left with 1 half. So again, big fat yes, you must have a common denominator for adding or subtracting fractions or anything else. You must combine like things. Multiplying and dividing, you get a little more freedom. So with multiplying, you're going to just straightforward multiply the numerators, multiply the denominators. That gives you 8 for your numerator and 21 for your denominator in our example. I just multiplied straight across. And again, no, we don't need a common denominator for this one, only adding and subtracting. When we divide, it's not quite straightforward until we turn it into multiplication, and the way we do that is change this into multiplication and flip this around. Then it just becomes that straightforward multiplication problem. So here, we're going to keep, change, flip. And now we can just multiply 12 over 14. However, with 12 over 14, this isn't in its lowest form because there's a common factor of 2 that I can pull out of both. And when I pull out any of their common factors, that makes my fraction smaller, which is what I want to do. And there's no more common factors between 6 and 7, so I know that I'm done with my problem. And again, for dividing or multiplying, we don't need a common denominator. And once we turn dividing into multiplying, it becomes really straightforward. Here for the fraction raised to an exponent, we're just going to distribute. So here, I'm going to distribute the 2, both in the numerator and the denominator. 5 squared is 25. 11 squared is 121. Let's take a look under the hood here. So this is telling me I'm going to be multiplying some base 2 times, put that in parentheses. And then the base that I'm multiplying is this fraction. And so when I multiply the numerator and I multiply the denominator. And so you see I got the same answer. So the shortcut is just that. It's a shortcut. You can apply this to here, and now you're good. And really what's going on is that you are just multiplying across twice and multiplying across twice. So when we need to reduce a fraction, we look for the greatest common factor. And when we need to add or subtract fractions, we look for the lowest common denominator. There's a method called the cake method, and this is a method that I used when I was first starting out to help me find not only the greatest common factor, but also the lowest common denominator. Let's look at an example. So we have 72 over 180, and we need to reduce that. So I'm going to take the 72 and the 180, and I'll put them on either side. And of course, you don't have to draw the cake. You could just draw a line between the two of them there. I just like to be a little extra. So the first thing we do is look for a common factor between 72 and 180. And that's going to be, well, 1. They're both even, so I'm going to pull out a 2. Is it the only factor? No. Is it the greatest? No, but it's a common factor. So we'll get to the greatest. So 1 factor is 2. 72 divided by 2. That's going to get me 36. And then if we have 180 divided by 2, that's going to get me 90. And now for the next layer of cake, I'm working with 36 and 90. So those are also, again, we're working with even numbers. And so we will pull out a 2. 36 divided by 2, that's 18. And 90 divided by 2 is 45. So now I have choices. I can pull out a 9, which if you're trying to get straight to the answer, you're pulling out the biggest thing you can find. However, if you want to do prime factors, just keep pulling out prime numbers. So 3 is another prime number. That's a factor for both 18 and 45. 3 times 6, that's 18. 3 times 15, that's 45. So there we go. Now we can pull out one more factor. 6 divided by 3, that is going to give me 2. And 15 divided by 3, that will give me 5. So for 72, we have 2. For 180, we have 5. And for the greatest common factor, we have 36. What do we do with those? Well, we divide 36, and we divide by 36, which 36 over 36 is just 1. So we're really just dividing by 1. We're not changing the value. But what we will do is change the name into something smaller. And so 72 divided by 36, that's our first number here. And 180 divided by 36, that's our number here. And so we end up with a reduced fraction of 2/5. So the greatest common factor is found by multiplying everything in this column. 2 times 2 times 3 times 3, which is 4 times 9, which is 36. So now if we need to find the lowest common denominator, we're going to take that 36, that 2, and that 5, and we'll multiply them all together. So the greatest common factor times these things here that we got from taking out all of those factors, 360 is our lowest common denominator. Let's look at an example problem. So let's do 572 and 7 out of 180. So we can't add those together. There's no way to do that. 70 seconds, 180ths, those are not things that the brain does easily, so we have a better way. We're going to give those our common denominator, which we found of 360. And denom, the name, it's French. So the name we're going to give this now is going to be 360. And in order to get to 360, we had to pay a price. We had to multiply times 5, so we better do that to the top and the bottom. Because essentially, what's 5 over 5? 1. So we're just multiplying by 5 over 5, which is multiplying by 1. We cannot change our answer when we multiply by 1, but we can give it a new name, denom. So to get 180, we have to multiply by 2. We have to pay this price over here. So 5 times 5 is 25, and 7 times 2 is 14. And now, because they have the same name, we can add them together. 25 of something plus 14 of something is going to be 39 of that something, and we can reduce the 39 and the 360 by dividing both top and bottom by 3, which gives us 13 over 120. Fractions where the denominator looks like this, or reducing where you're faced with these two numbers, and you're going to do the same method that you did in the beginning until we no longer have factors, and we will combine what we have to get our greatest common factor or our lowest common denominator. So for here, we're going to start with the 24 and the 12. And so from the 24 and 12, they have a greatest common factor of 12. To get back to 24, we multiply times 2. And to get back to 12, we just multiply times 1. For the x's, we're going to pull out 3 copies of x since there's 3 copies in both. And so for x3, if we pull that out, we're going to be left with 5 copies on this side. And we're going to be left with, we pulled them all out, so just times 1. Now for y's, we've got 5 y's on this side, and got 6 on this side. And so you can see, we can pull out 5 from both of them. And what we're left with, let's make the right letter. When we take out 5 copies of y, we just have a times 1. And here we've got 1 more copy left of y because we had 6. Over here we just had the straight 5 that we're pulling out. So last, we'll pull out z, and that's a copy of z is on both sides, so that's nice. So we're just left with times 1 and times 1. So we never write times 1, right? We always just leave that alone. So what we're going to have down here, we're going to have 2 times x5 times 1 times 1, and I'm not going to write the times 1s. Here we have 1 times y times 1, which is just y. And so the greatest common factor for both of those is going to be 12 times x3. And then let's see if I can get my pen to work. Times y5 times z for our greatest common factor. And then we would multiply times that to get back here. And we would multiply times that to get back here and double check. And so if we needed to use the lowest common denominator, greatest common factor, well, the lowest common denominator was going to be to add all of these things up. So 2x5 is 24, x8, and then y5, and this y here is y6, and then z. So remember, when we multiplied this times this times this, we got our lowest common denominator. And if we wanted the greatest common factor, that was simply this column here, just like with our cake method, with just numbers and not any letters involved. So it's the same exact technique. So down here, I've identified a couple properties that we're using. So on the right-hand side, we have identity, and that just means multiplying times 1, you're going to get back what you put. And the way to get 1 is having the same, whatever you have in the top, have it in the denominator, and that's going to get you back to 1. For square roots, one thing that is interesting is a square root can be undone by a square, and a square can be undone by a square root. So let's just put x here. And so this square and this square root, they cancel each other, and you're just going to end up with x. So this square and this square root, they cancel each other. I'm just going to end up with x. So for this here, if we want to take the square root of x squared, or the square root of x and square it, that's going to get us x. Square root of x times the square root of x. Remember, that's this squared. This thing and this radical cancel each other out, and I just scribble them out when I see them together. Whenever I see a radical and a square, I'm like, oh, they are going to just leave me with this x here. So we're going to use that property to rationalize the denominator, which is the last thing you're going to have to do with fractions. probably all the way through your sophomore year of college. So let's take an example problem. We want to do 5 over the square root of 5, and we want to multiply that by some version of 1 that gets this radical, this square root of 5, out of the denominator. You can have square roots in the top, but you can't have them in the bottom. So we're going to use that principle that if we have a square root squared, right? So a square root squared means to put that square root twice. Now we've got it squared. That will cancel everything and leave us with just the 5, but of course the price to pay is up here. We have to do the square root of 5 on the top and the bottom. And there's nothing to do with that. We just put 5 square root of 5. One thing we notice, I don't see any pluses here, so I can take divide by 5, and the final answer here is the square root of 5. So when you're rationalizing the denominator, you need to just multiply by the exact same thing, and that's going to be a square. When you have the same thing twice, that's a square, right? 5 times 5, well, 5 times 5 is 5 squared. And if you take the square root of 5 squared, you're back at 5, right? The square root of 25 is 5. So the square root of square, you're back where you started. So that is going to be the notebook section on fractions.
Hi friends, click the link in the description for all of the worksheets that go along with today's video, and if you want to go through the notebook from the beginning or dive into another topic, check out the other videos on the channel. And of course, it wouldn't be a YouTube video without the obligatory begging, so I put a lot of effort and time into this. I just want you to get something that's not a random AI generated, blurb of nonsense. I really want people to learn, and so I can continue to do that if you can continue to support me. And so I would love a like or a subscribe, anything that helps the algorithm. And if something clicked or if something confused you, or if you want to dig into something I haven't covered yet, say so in the comments. Thanks for watching, and we'll see you on the next page of the notebook.